Welcome to CDR Horizons, a new series from OpenAir, hosted by Charles and myself, Harsh, in which we engage leading researchers about novel carbon removal technologies and ideas that they're developing. CDR Horizons will explore the future of removing carbon dioxide from the atmosphere, and we're excited to have you on this journey.
In this episode, we speak with Sonja Salmon, an associate professor in the Wilson School of Textiles at the North Carolina State University. We learn more about her work with carbon capture that combines biological enzymes with textile substrates. If you're interested in following breaking carbon removal research, definitely like and subscribe to our channel for more content. And now, on to the show.
Thank you, Harsh and Charles. Thanks very much for this opportunity to talk about the biocatalytic textile technology my team is developing for CO2 capture, and I really appreciate all you do to raise awareness about CDR technologies. So the technology my team is working on falls within the carbon capture technology arena called reactive absorption. Reactive absorption is especially useful for separating CO2 from gas mixtures at atmospheric pressure conditions. And this would be the pressure conditions like you find in upgrading biogas. So in upgrading biogas to renewable natural gas, you need to remove the CO2 from the methane so that you can have purified methane for putting it in pipelines. Or removing CO2 from atmospheric combustion power sources like biomass power, where you would burn wood chips, or for natural gas and coal power, where these power facilities would be operating with the flue gas emissions coming out at atmospheric pressure. So here's a schematic, a simple schematic of what reactive absorption system looks like. You have a gas mixture entering the bottom of what's called an absorber. And here we're showing CO2 and methane. The gas travels upwards through the absorber. Meanwhile, a liquid is pumped through to the top of the absorber and travels downwards. And inside the absorber is what's called packing material. This is often stainless steel material with lots of holes in it that allows the liquid to spread out and allows a path for the gas to travel through so the gas and liquid can come into contact. Now the CO2 will react with this liquid, and you choose a liquid specifically that reacts quickly with CO2 and only with CO2. So it picks up the CO2 gas into the liquid, and then all of the gases that do not react with the liquid can be emitted out the top. In the case of methane, you'd actually catch this in a pipe. Or if it was just a combustion emission with nitrogen, you would vent it to the atmosphere because nitrogen is harmless. But now you've picked up the CO2 in this liquid and you carry it to the next stage where you're going to recover the liquid because you want to reuse the liquid over and over again. So you pass the liquid again through some packing material in the desorber, and the desorber typically is operating at a high temperature, at the boil basically, and using steam and the heat to strip the carbon dioxide back out again. And so what you have now exiting this part, the desorber, is you now have a purified stream of CO2, and you can put that into a pipe. And so you've captured the CO2. It's no longer going to get out to the atmosphere. And then once you've removed the CO2 from the solvent, you can send the solvent back again. And so it runs kind of like a figure eight. So to reiterate, the CO2 from most biopower and energy sources is operating at atmospheric pressure. That's why you need solvents that can react quickly with the CO2. And reactive absorption is considered to be the most effective method for carbon capture at atmospheric pressure. The CO2 is separated into the liquid, and then the liquid is move to the desorber, where you release the CO2 into a container like a pipe, and you reuse the liquid. So that's the principle of reactive absorption. But do note the temperatures. You have an absorber side that's running at about 40 degrees Celsius and a desorber side that's running at about 100 degrees Celsius or more. So it's pretty hot in there. So the good news is reactive absorption works. And one particular type of solvent containing monoethanolamine works really well. This compound reacts very fast with CO2. And so it's quite efficient, and you can build absorbers that are not impossibly tall. This technology has been used for many years in the oil and gas industry, and it's, as I mentioned, very efficient. The bad news is it requires a lot of energy. So when MEA reacts with CO2, it's an exothermic reaction. It releases heat. And then you have to pump all that heat back in again when you want to recover the CO2 from the solvent. And that heat is requiring a lot of energy. So what if we could do this, but just get away with using solvents that require less energy? And such solvents do exist. They are in a couple of different categories, such as tertiary amines and carbonate-based solvents. So these are compounds that can react with CO2, but the rate of the reaction is very slow. So what if you could speed up the rate of this reaction? And this is where enzyme technology has the potential to help. Throw a little biotechnology into this very complicated chemical engineering system. So enzymes, in case you don't know, enzymes are nature's catalysts. They are responsible for making nearly all the essential chemistry of life possible. They are complex protein-based molecules that have a special three-dimensional structure called an active site located somewhere within the protein. And this active site has special features. It only allows certain types of molecules to enter, and it has special chemistry at the active site that does what catalysts do, and that is lower the transition state for chemical reactions to occur. So here is a kind of a cartoon of an enzyme called carbonic anhydrase. This enzyme actually happens to have zinc at its active site. And the enzyme catalyzes this reaction right here. CO2 plus water equals bicarbonate, plus it releases a proton. And the enzyme actually catalyzes both the forward and the reverse reaction. So depending on what the driving force is, you can go in the forward direction, that is to say, make bicarbonate, or the reverse reaction and release CO2. So for absorption, if you have an alkaline solution that can neutralize this proton, you can push this reaction in the forward direction. And so by doing that, you can use this enzyme in a suitably alkaline liquid to selectively convert a poorly soluble gas molecule. CO2 does not like to dissolve in water, but you can take that, you can hydrate it using this enzyme to bicarbonate, which is a highly soluble component. It's an ion. And thereby, because the reaction is only with CO2, it will selectively remove CO2 from a gas mixture. This has been tried already. This is not a new idea. Actually, the idea itself is more than 50 years old. So there have been a number of lab and field tests published that show that carbonic anhydrase improves CO2 absorption efficiency of these low energy solvents. However, the enzyme can't do the whole thing by itself. It needs a solvent to work with. And also the enzymes, they're proteins, and exposing proteins to high temperature can cause problems. They may become inactivated and not work anymore. So you need to adapt the process to maximize the benefits. And one way to do this would be by enzyme immobilization. So why do I think enzyme immobilization would work? One of the reasons is because we tried doing this without immobilized enzymes previously. And here is some of that original data. This is from a study that was funded by the Department of Energy, where a collaboration between Novozymes, PNNL, University of Kentucky, and Dusen Power Systems worked on running a bench scale trial where carbonic anhydrase enzyme made by Novozymes was simply dissolved into the solvent. So this was a potassium carbonate based solvent. And when there was a lot of replenishment of enzyme, when you could simply keep putting enzyme in, actually the system worked pretty well. You know, we were at that time targeting 90% capture, and it came pretty close to that. However, when you stopped replenishing the enzyme, the performance dropped very quickly. And that's because of the high temperature in the desorber. The enzyme simply couldn't tolerate that. It was kind of cooking like an egg. So this gave us the idea that, well, we really shouldn't be letting the enzyme travel through that desorber. What if we kept it in the adsorber, where it was actually doing the most good? So the benefit was the enzyme definitely catalyzed the reaction. The challenge was the replenishment rate, and this is where this idea of immobilizing the enzyme comes in. We are also not the only ones who have immobilized carbonic anhydrase. Others have done it too, and some quite successfully. But more work is still needed because this hasn't gone commercial yet, and so it still needs attention. It still needs thinking about how to do it in a good way. So the concept we are working on, we call it biocatalytic textiles. The concept here is that we're going to create contactors using textile fibers. And these textile fibers will be a new kind of packing material that will allow very good gas-liquid contact, and it will hold the enzyme where it needs to work in the absorber. And the textile will also participate in controlling the behavior of the liquid flow. So if we choose a textile that likes to absorb water, for example, we can actually direct the fluid flow, which could be very helpful in this technique. So this was a very early kind of schematic picture of what it might look like if we took carbonic anhydrase enzymes and we trapped them or attached them to polymers, and then we would attach these polymers to a kind of filter, and that filter would catalyze reactions, like in this case we're showing a biogas mixture, methane plus CO2 plus water. You'll trap the CO2 with water in the solvent, and you'll end up with purified biomethane. So that was the idea, that you could do this reaction and use solvents that were less energy intensive than MEA. So how to make these contactors? Well, we're starting with enzymes, which are very environmentally friendly, sustainable types of materials. They're proteins, they're made from natural raw materials, and they're biodegradable. So our thinking was that we wanted to find immobilization matrices that had similar sustainability profile. So being in the College of Textiles and working with textiles and knowing something about how they work and why they work, it occurred to us that actually cotton would be a pretty good candidate as an immobilization matrix. The pH of these solvents for carbon capture is always a bit on the alkaline side. And cellulose, whether you knew it or not, actually tolerates alkaline conditions pretty well. The carbonic anhydrase enzyme itself also tolerates alkaline conditions quite well. So we just needed a way to attach the enzyme to the cellulose, and for that we went to another biopolymer, also a polysaccharide, called chitosan, which has the attractive feature that you can dissolve chitosan in dilute acid solutions rather easily, and then you can apply it, so you can mix enzymes together with chitosan, you can apply it onto the cellulose, And once you expose this to an alkaline condition, this protonated amine group will become deprotonated and it will not be soluble anymore. So you have a good way of fixing the enzyme onto the cellulose material. Another good reason to use cellulose, it is actually polymer number 1 on Earth. If you didn't love cellulose before, you should love it now, because there is more of this material on the Earth than any other biological compound. So it's good stuff. Here's a picture of what we made. We decided to use a fabric, and we didn't just use t-shirt fabric. We thought a little bit. We've got to get gas flowing through here pretty easily. We need to let the gas and liquid run up against each other. So we chose a fabric like cheesecloth, like what you might have in your kitchen that has a lot of holes in it. And that's pretty floppy material, so we needed some kind of rigid support. So we had a more stiff material that we placed it on. So that's what the double grid background here is. The fine grid is the cheesecloth, and the larger grid is a more stiff material. So we created this kind of sandwich, and the idea would be that you would have a gas mixture kind of flowing up through these filter materials, and you would actually have liquid absorbed inside the yarns. And as the CO2 interacts with the enzyme that's entrapped or embedded on the textile, you would form the bicarbonate, and that would just get carried away with the liquid. On the right-hand side here, this is a much closer up view of what a cotton fiber looks like. So here we're looking kind of macroscopic, and if you zoom down, an individual cotton fiber is about 20 microns in cross-section, to give you an idea. And then the enzymes themselves, you can't see them here at all. They're very small. They're about 3 to 5 nanometers in diameter. So we're really just looking at the surface of the cotton fiber and believing that there are enzymes there. But we know that because we tested for the activity, and we can tell that these materials have biocatalytic properties. So our results with our generation 1 packing, we tested this in a small column that we have in our laboratory. So it's just the first half of the reactive absorption system that I showed earlier. So this is just the absorber column, where we pass what's called lean solvent, that is to say solvent that's not loaded with CO2. We pass that in through the packing material, and then we blow a gas mixture up. And then we can measure with a CO2 analyzer how much CO2 is remaining in the vented gas stream if we start with something that's around about 10%, which would be similar to what's in a combustion flue gas from coal, for example. So here is what our little contactor looks like in real life, and an example where we put the biocatalytic textile module inside. Earlier, it looked like a sheet, but when we put it into this column, we actually roll it into a spiral, and we put some spacer material in there so that the liquid and gas can pass next to each other without flooding. It's called flooding when they get kind of stuck in there. So we've designed these to be flooding-free modules. And the liquid actually spreads very beautifully throughout the packing, making a very nice uniform wetting. And that's hard to achieve on other types of packing like stainless steel. So this is really a special benefit of the textiles, is their ability to spread the water naturally by their inherent properties. Here are some results where you see the CO2 capture efficiency on the y-axis. The numbers themselves are very arbitrary in the sense that it really depends on how you've set up the experiment. So these just should be viewed as kind of relative numbers. Our gas flow rates in the lab scale are actually pretty low. So you'd have to build bigger contactors basically to accommodate higher gas flows. But if you look at this from just a relative perspective, you can say, well, if we put in standard conventional, what's called random packing, in this case, they're called Raschig rings. They're little glass kind of tubes, little elongated donuts. If you put those in, almost no CO2 was picked up, and there was no enzyme in that system. if we put just one of these textile packing modules in, like you see here in this picture, just the textile itself without enzyme on it, it actually works quite a bit better than the conventional packing, just because you've increased the surface area and made that gas liquid contact better. And if you stack two of them together, one on top of the other, then they work even better. So you have this idea that you could scale it simply by making them bigger and taller. And then if you put enzymes on one of the packing, you can see it actually works 2 times better than the textile by itself. And if you stack two of those together, it works better. So again, we have a scalability idea. And then interestingly, we put, just for comparison, we put dissolved enzyme in the liquid, not on the packing material, but just in the liquid, and let it run over one packing material. And it still performed the best of all, which gives us reason to believe that if we still improve the way we immobilize the enzyme on the packing, we'll actually be able to get it to work even better. Interestingly, you do see a little lag here with the dissolved enzyme that you did not see with the textile packing. So it actually took a while for the enzyme to distribute through the system relative to the packing, where the enzyme was already distributed throughout the system, which is an interesting note. And then we took the textile packing with enzyme, essentially this green sample right here. We ran it some more for about 5 days to see how stable it was. And after an initial decrease, it ran actually fairly stable for that period of time. But we didn't necessarily like that decrease, so we went to design a generation 2. And in the generation 2 design, we included cross-linking agents to attach the enzyme more firmly to the surface. And we tried quite a few different versions here. If you want to know more details about that, we do have a publication came out recently on that. So our first version was just enzyme kind of trapped in the chitosan coating that was on the fiber. And our generation 2 that we decided to scale up and do more testing with was one where we used cross-linking agent to attach enzyme really to the surface of the chitosan as these aggregate materials. So we had pretty heavy loading of enzyme on the surface. Using that version, we get these kind of results, which are pretty nice. So we have a test example with 1 cycle of operation. Again, these are a bit arbitrary units, but you can see that when the enzyme is present with an absorption solvent, it works much better than with tap water alone. So I wanted to emphasize that the absorption solvent absolutely is critical. You can't just do this in pure water. You need that alkalinity. So as long as you have the right enzyme, the right absorption solvent, the right packing material together, you can get it to work. And here we stressed this particular packing material with 10 cycles of testing and even incubated it for 100 hours in a solvent at 45 degrees and tried it again, and it retained 100% of its performance. Then we took it, we dried it, and we stored it for a year at room temperature and pulled it out again and tried it, and it did pretty well. So we are very pleased that these are not fragile materials. They can withstand quite a bit of abuse, even having them lying around unattended. And this same packing material, we then ran it for a 500-hour test, which is about 20 days. And as you can see, the performance was very good over that period of time. So we're really encouraged by these results. We also were interested to know whether the packing could work with other concentrations of CO2 than just what you might get out of a coal-burning power plant. So we tried it by decreasing the CO2 concentration down towards 5 to 6%, which is like what you would get in a natural gas-fired power plant emissions. And it works. And we raised the CO2 concentration up towards here 30%. Biogas maybe has 40% in it. Also worked. We can see a decrease. So when you have more CO2 going through the system, that actually puts some stress on the solvent to be able to carry that much. But if we increase the delivery of solvent by increasing the liquid, what's called the liquid to gas ratio, if we just pushed more solvent through the system, we were able to pick up more CO2. So these data show that the system is quite robust to different operating parameters. And then we also want to be able to take CO2 out of air. I know the point I've emphasized the point sources, but sometimes being able to pull CO2 out of air will be very advantageous, especially if you can do that near one of these sink locations where you can sequester the CO2 easily. So we tried it. Oops, sorry, I went too fast there. And here is our direct air capture experiment in an indoor environment. So when you're inside, even though we all maybe have committed to memory by now that global average CO2 is around 400 parts per million. When you're inside, you're actually breathing more because of you're breathing out CO2. So in our lab, the CO2 concentration indoors was around 700 to 800 parts per million. But we used that as our inlet gas. We used seawater as our solvent because seawater has some alkalinity in it. And we ran that seawater over our packing material and are happy to show that not only could we pick up the CO2, we actually were able to get the CO2 level below the global average level. So this tells us that actually the system, even though we didn't try it outside, it should actually work outside. Now with this technology is we are collaborating with University of Kentucky again, and they have a nice bench scale system there where we make modules, and we have sent some of our modules to them for testing already, and we're going to run another round of testing in the coming year where we will be collecting information on what the energy requirements for this system are. So I don't have that for you yet, but we're looking forward to these results. And once we get these results, we will be looking forward to moving from as where we are now, lab scale, getting more bench scale testing. And we would love to find opportunities to test this out in even larger scale, maybe a small field test with biogas upgrading or some similar industrial application, shooting towards a longer term when we can go after a full-sized power plant. So all this effort, actually, it was a lot of effort. Over many years, I've been working on this type of thing for quite a while. And I so deeply appreciate all the people I've worked with. One doesn't do these kinds of things alone. It takes a lot of collaboration by people who care and often do things just because they want to, not because somebody's telling them to, but because they want to and they feel it's the right thing to do. So we're very fortunate with our current collaborators, Novozymes, the good folks at NREL, and this at the University of Kentucky Center for Applied Energy Research. And we appreciate very much the funding from the Bioenergy Technologies Office of the Department of Energy, which has made this work possible. If you want to know more about what we're doing, please drop in at our website, our Textile Biocatalysis Research team. There you can find links to our publications, and you'll also see what else we do. So thank you again.
So thank you so much for presenting, Professor. That was really fascinating. The one thing we like to start off all our podcasts with is just learning a bit more about you and how you got interested in this topic. So what was your journey till here and what got you excited? about working on this?
Well, actually, my journey began many years ago. I've been doing this for more than 15 years. That I first encountered the possibility that you could use enzymes in a good way for carbon capture. I was working for Novozymes at the time, and I was fortunate to be working on an innovation team. So my advice to anybody who's out scouting for new ideas is, form your innovation teams, form your groups that do brainstorming together, make a little cluster of people who can act on a good idea when it comes up. So I was part of a team where one member of the team got contacted by someone who was asking about carbonic anhydrase for CO2 capture. And at the time, I actually had never heard of it before. But fortunately, I was making a trip shortly thereafter to an annual research meeting where the whole purpose of the research meeting was to get together with other colleagues, collaborate with them, and talk about new ideas. And so over lunch, I'm serious, nearby, have you ever heard of this before? And somebody said, well, I haven't, but I know somebody who's been talking about it. So why don't you get in touch with him? And that turned into a momentum. Just, then it became the passion project. Then it became the curiosity, like, how can we get this to work? Because at the time we had nothing. we didn't even have an enzyme that worked. So there was a big effort to make enough enzyme so that the usual question is, can you even make this enzyme? The answer is yes, you absolutely can. So that's not the gap anymore. The gap is to show that it can outperform other technologies now, and that still needs some effort. I'll put a little PS there. You say, like, why the textiles? Okay, actually, I'm a graduate of the Wilson College of Textiles, Fiber and Polymer Science. I'm just fascinated by fibers and polymers. They're just so interesting to me. They're lightweight, flexible. They have these interesting properties like moisture absorption, and nature relies on polymers to make all these beautiful materials that we use. So it's actually, you could say, my hobby is sewing. And so it became very natural for me to think about, well, why don't I stick some enzymes onto something I could sew?
Wow, that's fascinating. I think we see a lot of innovators and people who are doing really kind of groundbreaking stuff in this field. Their research just combines a lot of their diverse past experiences and interests, and it just somehow comes together so beautifully.
Yeah, that's super. I was actually just about to ask about the textiles part, because I feel like we don't hear about that very often these days. But it's very cool to see something that we might take for granted is so interesting and can be used in so many different ways. I was curious to hear more about this enzyme, because my understanding is a lot of folks who are working on this kind of direct air capture stuff or carbon capture, not many of them are really focused on kind of the biological approaches or perhaps enzyme-based approaches. I'm curious if you have any thoughts on that perspective. I know some other people have tried doing catalyst immobilization, inorganic catalyst immobilization, but it seems like you're taking a very different approach. Do you have any thoughts on that comparison? And you already briefly discussed this, but how do you see these things panning out?
Yeah, actually, there's actually a maybe it's a pretty close-knit, tight community spread around the world that knows about the enzyme technology, but it could easily be that many people don't. And so certainly that's a great advantage of being able to talk to you today, is kind of get the word out a little bit more. One obstacle is that the enzyme is not, well, you can buy small quantities for high prices in a research catalog, and that can be quite off-putting to people. So if you want to pursue the enzyme technology, then you have to kind of build up some partnerships with the people who can make it in large scale. And that, I think, is one of the bigger gaps. But part of it's also just being familiar with the technology. So, and I admire people who are using other technologies for carbon capture, technologies that I wouldn't know how to begin with it, but it's their comfort zone, and that's what they do. And so, I mean, folks have even, talked about, well, and even tried it, can you put enzymes together with things like MOFs, which are also used for carbon capture? Like, can you start putting some of these technologies together? And I only imagine that, yes, that's going to happen, and more as more people get familiar with what the different materials can do.
I guess in terms of enzymes, and as we saw some of the research you had on different enzymes and like how many layers you have and the effectiveness, is that something you're still experimenting with, like trying out new enzymes or new materials, or do you think this is kind of at a good place where now it's about proving this and scaling it up?
Oh, there's still a lot to do, but I think this is what has to happen for carbon capture is we need to be doing both at the same time. We need to be continuing the fundamental research and scaling up at the same time. We don't have time to do it in a straight line. We got to mix it up and do it all together at once. For the reason why I talked about the reason why I told this story about the Gen 1 and the Gen 2 is I wanted to tell that little bit of story that there is development to do. We've only scratched the surface on what kind of textile designs that we could make. So there's years of work that could go into that. On the enzyme side, you could still engineer and make better enzymes. So that one also that's not nearly at its end point. But what we have already in hand is we have things that are good enough to take it to the next stage and good enough to start proving it out. And that, I believe, is what's needed with any technology that can get to that. It's good enough stage. We need to get it out there and learn what really has to be better about it so that we can work on those things and make it as good as it can get.
Yeah, I think there's some iteration there, right? Like once you have it in the field, that's really when you nail down the weaknesses or areas of development.
Yeah.
Yeah, I really appreciate that perspective, because I've heard a lot of folks, it's a very short timeline. It's a yes and kind of on one of your slides. Mm-hmm. It's a yes and kind of thing. We need to do everything all at once. You've shared a little bit about like kind of your journey in this research and development. I'm curious also about like how you found collaborators. What was the story kind of there? You've talked about folks at University of Kentucky and National Energy Technology Lab. How did those things kind of all like come together in that kind of network?
Who could ever tell? It's when an opportunity shows up, you got to grab it then, and it never comes at the right time, but you got to grab it anyway. And I'm just going to with deep appreciation, echo something that a colleague told me a long, long time ago when I was kind of new in the working world. And this was before text messages, I tell you. Pick up the phone. Just pick up the phone and call people. Sit down at lunch and talk to people. That you got to talk. You got to be willing to share your idea, even before you know how to tell what your idea actually is. So you got to trust that people aren't going to laugh at you, or if they laugh at you, it's only going to be for fun, right? So you have to, and then of course you gotta be ready to pick up the pieces when things don't go right. The project I worked on for these many years has closed more times than I can remember, but I that's why when people talk about their passion project, I understand, because this is my passion project. I'm going to work on it somehow.
Yeah, I love to hear that passion and drive, especially in academia. I feel like it can be hard to find the right niche that occupies your interests. So the closing question that we usually like to ask our guests is, we're part of Open Air Collective, which is a community of policy advocates and also open source researchers and designers. Are there any ways that our community can help you along in your journey and in your research and work?
Wow. Yeah, I've heard that mentioned in your other shows, and I've been reflecting on it. I think I know a gap that I experienced myself is on the economic analysis side. I don't really know how to do that myself. That's not my area of expertise. And I don't really know how that is done as an open source either. It seems like the techno-economic evaluations tend to be rather specialized, but if such a thing exists and there are people who would like to talk to me about that, I'd love to chat on that. I mean, the other thing clearly that I'm interested in, I'm looking out for partners who would be interested in trying to scale this up, and scaling up always takes resources and skills and competencies that not any one person or organization necessarily has. All I can say there is I'm used to working with a lot of people on a lot of different things simultaneously to try to make things happen. And so I'm also interested in hearing about opportunities for scale up. If there's a spot that would like to try it, I'd love to talk with them.
Mm-hmm. Sounds good. We will definitely put out the call. And thank you again for taking the time to chat with us. This was a really interesting talk.
Yeah, thank you so much. This was amazing.
Well, thank you. Thank you very much for your time and all that you do.